Hey everyone, tell me this, have you ever covered your ears while someone was drilling nearby and still felt the vibrations in your head? That's sound energy at work. Sound doesn't just pop into existence, it travels through something. It needs a medium, like air, water, or even a solid wall, to make its journey from the source to your ears. Imagine this, you drop a stone in a pond. The ripples spread outward, but does the water itself move to the other side? No. The energy moves, not the water. That's exactly how sound travels. Each air particle jiggles back and forth, bumping into its neighbor, like a relay race of tiny, invisible runners passing energy down the line. The particles themselves don't go anywhere far, they just shake in place, and the disturbance, the wave, keeps moving until it reaches your ear. So, sound propagation is really energy on the move, not particles migrating across space. Pretty neat, right? Now, let's zoom into what kind of wave this actually is. Whenever a tuning fork or guitar string vibrates, it pushes the air particles in front of it closer together, forming what we call a compression, a region of high pressure. Then, as it swings back, it creates a rarefaction, a region of low pressure. If you could slow this down and actually see it, you'd notice alternating squished and stretched layers of air, compressions and rarefactions moving out in a wave. This is why we call sound a longitudinal mechanical wave, because the particles vibrate along the same line as the wave travels. They move forward and backward, parallel to the direction of energy transfer. So next time you hear thunder rumbling far away, remember, it's the dance of compressions and rarefactions in the air, racing towards you at hundreds of meters per second. Okay, let's make this even more visual. Ever played with a slinky? And yes, it's still a scientific instrument in our lab today. Hold one end, let your friend hold the other, and give it a quick push. You'll see the coils bunch up in one region, that's a compression. Then they spread out, that's a rarefaction. If you mark one coil, you'll notice it doesn't travel along the slinky, it just moves back and forth, parallel to the wave's direction. That's exactly how air particles behave when sound moves through them. So, the slinky is basically sound in slow motion, just less noisy and way easier to photograph. Now, let's talk pressure, not the exam kind, the air pressure kind. When sound travels through air, it causes alternating regions of high and low pressure, like an invisible accordion expanding and contracting. At the compressed points, air molecules are tightly packed, that's high pressure. In the rarefied regions, they're farther apart, low pressure. If you graphed this, you'd get a beautiful wave, crests showing compressions, troughs showing rarefactions. The distance between two consecutive crests, or two troughs, is the wavelength represented by the Greek letter lambda. So, in essence, sound propagation is really just a moving pattern of pressure changes, invisible, rhythmic, and all around you right now. Now that we know how sound travels, let's break down its three main features: frequency, amplitude, and time period. Frequency, denoted by F or nu, is the number of compressions or rarefactions passing a point every second. You can think of it like the beat of a song, faster beats mean higher frequency. Time period, represented by T, is just the opposite. It's how long one full vibration takes. They're related by a simple but powerful equation, F equals 1 divided by T. Amplitude, on the other hand, is how far the particles move from their resting position, and it decides how loud the sound is. Bigger amplitude, louder sound. So the next time someone plays loud music next door, you can scientifically say, hey, your amplitude is way too high. Alright, moving on to how fast sound travels. Sound speed, represented by v, is just distance divided by time. Mathematically, v equals lambda multiplied by frequency. For example, in air at 22 degrees Celsius, sound travels at roughly 344 meters per second. That's fast enough to reach the back of your classroom before you finish saying sound. But remember, it depends on the medium. In solids like iron, the speed can go up to nearly 6,000 meters per second, while in gases like air, it's much slower. Why? Because particles in solids are tightly packed, so they pass the vibration faster. And if you've ever seen lightning before hearing thunder, now you know why. Light races ahead at 300,000 kilometers per second, while sound trudges along at just a few hundred meters per second. So, let's wrap this up beautifully. Sound is nothing but energy traveling through vibrations. Particles don't go anywhere, they just jiggle in place, creating compressions and rarefactions that move the energy forward. It's a longitudinal wave, meaning the vibration and the travel direction are the same. The frequency decides how high or low the note sounds, the amplitude decides how loud it is, and the wavelength connects it all to speed. And remember, the medium matters, no air, no sound. That's why you can't hear an explosion in space, sci-fi movies. So, next time someone asks, how does sound travel? You can proudly say, through the elegant dance of vibrating particles, passing the beat of physics from one to another. Thanks for tuning in, literally. See you in the next session, where we'll make sound waves bounce back in the fascinating world of reflection of sound.